Thank you.
All righty. So next up we have Rob Stough and John Blevins from the SLS team. And Rob, hi, I can see you. Excellent. Are
Hello,
you going to be
Michael.
presenting the slides, Rob?
Well, John's going to kick us off here. I
Okay.
just want to say it's a privilege to be among you once again, to be interacting with the people that are going to solve the mysteries of the universe. So I would like to introduce our chief engineer for SLS, Dr. John Blevins. He is one of the most technical people, capable people I've ever met, and he is a wonderful speaker. So I'm privileged to be able to introduce him to you today. So John, could you chime in?
Hey, can you hear me okay?
Yes.
Yes.
Hey, with all the government restrictions, I have to confess this is the first time I've used Zoom in this format, so I'm glad to be here. And I don't know how to follow Rob's introduction, but I hope we can put the charts up. I want to talk about our vehicle today. I know this is a little different presentation, but I want you guys to know where we're at and our commitment to you guys as scientists that are solving these complex problems. We would love to fly your payloads.
Yeah.
So
And do you want me to share the slides, Rob? That was my question.
Oh, my apologies. Yes, I was hoping that someone would share the slides other than
I've
myself.
got them right here. I'll go ahead and do that.
Thank you.
Yeah, thank you, Michael. So as we get started, I'm going to tell you guys today a little bit about where we are with the vehicle. I think you'll be surprised at the progress we've made, not just on the first vehicle, but on the subsequent vehicles, where we're at as a program. And Rob's going to talk a little bit about how we can map that into those missions as soon as we can show these charts. And here we go. Yeah, let's get started. All right, let's go to that next chart. That background you see, and Rob's got that background on his, is actually our cargo, our biggest cargo vehicle. So I'm going to talk a little bit about our vehicle. We call vehicle evolution. It's really already underway. You know, on the far left side, you see what we call the Block 1 vehicle. This Block 1 vehicle will be flying it next year on a lunar mission, an unmanned lunar mission, to check out certain systems, including the Orion systems. I'm going to talk about the progress of that one. There is also this Block 1 cargo, and right now we're set to fly Europa on that, and we're well underway on that one too. And the fairings on that particular one are common with commercial vendors, and so what we provide is just more energy, and so that's kind of the uniqueness there. But one thing that's already underway, in fact, the meeting I just left, and I'll be going back to, although I've got a little more time than the noon Eastern, is on this Block 1B. We're doing a critical design review. If you're familiar with that stage in a program, we're doing the critical design review for the cargo of the Block 1B today. And most of those components, once we hit that point right there, when you see the SLS Block 1B cargo, virtually everything we need to do the missions we're talking about will be done, with the exception of what we call BOLE, our Booster Obsolescence and Life Extension Plan. We're kind of forced into that, as the name might imply, by losing some of the cases and the ability to use the heritage boosters from shuttle. But what it also forces us to do is improve performance. And so if you go all the way to the right, the vehicle that is most germane to this set of missions that you guys are interested in is this Block 1B vehicle. Right now, the funding and the programs are set to put that on for 2029, roughly 2028 maybe, depending on when all that manifest gets settled for lunar missions before that, right? So there's that human landing system, and that's a large part of what we do. But one of the things I want to show you that we do, and I want to go to the next page to talk about that just a little bit, is that we're a platform. I'm going to talk about this a little bit more. Yeah, go to that next page, Michael, if you don't mind. You know, one of the things that's happened with mechanical devices, and it's not limited to rockets. If you look at, say, the F-35, or you look at other complex systems, we've made them platforms, and we do multiple things with them. That's a little bit of a paradigm shift over the 1960s, if you think about it, with Apollo or anything else, where we built this very unique machine to do a very unique job. And ultimately, we're not doing that quite the same. We have more automation and more software-driven integration, right? The software is really the true integrator of the system. It's the one that sends the functional commands. And so anyway, so in thinking about SLS, we wanted to kind of propose to you how this goes. And I want you to think in terms of platforms, what it provides. And if you look at the top of this chart, what you see is that we give unrivaled mass. I know that there concept vehicles out there. There's even some in early development that are similar, but not nearly really the robustness and performance that we are able to provide, and the maturity, as I'll show you just a little bit. We provide a lot of these things that you see at the top. I'm not going to go through all of them, but it's the fact that we're a heritage manned system, right? A lot of this heritage comes from shuttle and before, right? So even the shuttle heritage, if you think about it, and I don't want to get too detailed, but the way we ignite the rocket engines, that comes from the Apollo ignition system for the J2. And so we've learned over the years, and we've been improved that. And those human-rated safety systems add a lot of robustness and really mission security and improvement to be assured that you're going to get there. What those things at the top do, though, is they enable all these things that you see at the bottom, right? If we get there faster and we don't do some of the gravity assist missions or go through different arduous environments, you can have a longer science mission life. Even if you had the same mission life, you can have a longer science mission life, because what we're going to provide is a quicker ride, more energy. And so you can see that middle section there, and that really starts to relate to what you guys look at in a tactical way, and ultimately from a philosophical way. This is just better science return and making missions that you couldn't previously do possible by using this platform, this SLS platform. So let's go to the next chart. So I get asked, is the rocket real? I'm glad Rob put this in our set of charts. You know, I actually got asked if NASA shut down after shuttle shut down. So clearly they don't know everything we do. And sometimes they forget some of the greatest contributions. In fact, what I'll suggest are the greatest contributions that NASA does. When I think of NASA, I think of some of the space telescopes and Voyager and some of the wonderful missions like Cassini-Huygens or the New Horizons mission. So one, NASA's still alive and well, and you guys proved that. And is the rocket real? The rocket is real. I'm going to show you pictures. Let's go ahead to the next one. I'm going to show you kind of the current state of the rocket. You may be surprised at how far we are down the road. There's hardware developed for the 6th and 7th and 8th missions that already exist, not just the first mission that exists. But I am going to focus a lot on the first mission here, because that's the one that I'm most concerned with, although I just mentioned I'm coming out of a critical design review for what is going to be the 4th mission or the 5th mission on the cargo Block 1B. Here you see the actual flight hardware. This isn't mock-ups. These aren't fit and check items. This is the actual hardware. If your zoom is such that, you know, our pictures aren't on your right hand blocking that right hand part, you see that we've actually put the NASA worm per the request of the NASA administrator on both boosters in the center segment. That's the flight hardware. It's under stacking right now. The solids are at the Kennedy Space Center, and you see the forward assemblies there with the forward skirts and all. And so this is not small hardware. This is some of our smaller hardware when you see the size of this rocket, but this is the same diameter of the original shuttle boosters. They are longer. And I wish I had a picture of the shuttle when I show the actual rockets. You would see the shuttle on that 2 slides earlier. You're just seeing the shuttle not even 2/3 the size of that final rocket, about half the size and stack of that final rocket. The final rocket is well over the size of our Saturn V or the Apollo stack rockets. So let's go, and I'll show you some more hardware as we go along here. Right now, we're doing what we call green run. And green run is kind of misunderstood as just a hot fire test. But in green run, if you're familiar with structural dynamics and structural design, there's a lot of certification that we want to do. This is a one-time shot in a program to certify the rocket, and we're certifying it for human spaceflight as well as other missions. And so the first test was a modal test. I'm going to show you just kind of a checklist as we go down. We've checked out TVC systems. We've checked out the interface of our software. You probably know, if you keep up with rockets, the software is one of the big issues. There's been recent software issues on manned rockets. And so all of that goes on during green run. The final 2 tests, though they are very dramatic, probably the most 2 dramatic tests are coming up. And so let's go to that next checklist. Hey, so what's interesting about this is I've been down there for some of these tests, and that first one was, you know, this is worded wrong, really. Applying forces. Everybody's got a countdown going and ready. Oh, we've got video. Okay, there you go. So this is some of the articulation of the nozzles and TVC and some of the other videos you see. But that first test is actually really important. It's not actually simulating launch. What it's doing is it's simulating forces or getting the deflections, the modal response that occurs during flight. If you're a mechanical engineer, have some history there, you understand that how important that is. But what's interesting, it was very non-dramatic. You know, we had bridge shakers that, you know, you use to shake bridges to get that modal response. They had 3 of them hooked up to the core stage, and they're running, and nobody can really visually see anything. But when we get to this final test, which is equally important, it'll be pretty dramatic. There'll be over 1 million pounds of thrust coming out the back end of the rocket and just huge billows of steam. Of course, you see that video. Those are Heritage RS-25s. Every one of those has some flight history. We've already restarted the line for flights 4 and beyond to put those engines on, and they're a little bit different. They're a little bit cheaper. So if you hear some criticism about the cost, we're addressing that. Sustainability is a big focus for us. So anyway, let's go to the next slide. Again, these are the segments as they're going on the left side. These are other parts of the vehicle. You probably don't care about the individual parts. I've got a schematic later in this setup that shows those parts. But the bottom line is everything but what I showed you in the core stage is sitting at the Kennedy Space Center waiting to be assembled. That core stage is the big new design effort, and it's the effort that got a little bit behind. And so that's the effort that we're going methodically through certification. It's, as I mentioned, it's a one-time shot, so there's been a lot of talk about skipping some of that certification, not doing that modal test that we did, not doing some of the other system checks that we're doing, but I'm keen on achieving that certification. And so we have stayed the course. We've, as I say, sat back in the pocket with the rush on like Joe Montana and waiting to deliver the pass. And I'm really going to be excited when that certification gets complete. And that green run, that test isn't just a start up the engines and shut it down. That's a full duration simulated firing on the ground, which has different environments than you would see in flight because you're sitting on the ground and you have a lot of reverberant energy there where as the atmosphere goes away, you don't in flight. So just a very interesting test we're doing, very robust set of tests. Let's go to the next one. All right, here's those segments that I mentioned. Everything but that core stage in avionics that's being built by Boeing with the engines attached to them, everything but that piece is waiting for us at Kennedy Space Center and has gone through nominal checkouts. We started stacking the boosters just a little, about 3 weeks ago. We went ahead and assembled what we could on each one of the sections. And then in order to get ahead on assembly, we went ahead and started stacking those boosters. All right, let's go to the next chart. Hey, so it's not just about Artemis 1. You know, if you're going to have a sustainable program, you know, that one-shot thing will get you a real nice maybe view on the History Channel and lunch with your buddies. But ultimately, our goal is to have a long-term sustainable space platform that can be used for all kinds of things. And that's what that original chart with cargo and crew, and that's a limited view. There's other cargo bearings you could put on there and that kind of thing. But in order to do that, you've got to have contracts and the infrastructure to go beyond that. And so that's a lot of what our program has spent money on and done, is getting that infrastructure in place and those contracts in place to get beyond the first 3 or 4 flights. We have enough residual hardware from shuttle to get the core stage engines for the first 4 flights. We've got enough residual hardware on boosters. As you know, we recovered boosters during shuttle. And so we've got all that hardware to get us through 7 flights, and that's when we'll start upgrading. And so we have gone forward with buying the parts and setting up the factories for the missions beyond that. So here you see some of those things, like for instance, on the boosters, we've already done the boosters through Artemis 3. So the second flight is a lunar flight. The third flight, we're not sure if that'll be a cargo or crew flight yet. It's not manifested. Those boosters are the same. They're already made for Artemis 1 being stacked, Artemis 2, they're already in storage, Artemis 3, they're ready to go. And that's not a limitation for us. We can do that in a hurry. We already have RL-10s, not just for the first flight and the second flight and the third flight, but we've already purchased RL-10s that'll go into the cargo missions that you saw on that earlier chart. And then the Artemis 2, you know, we're making the simple, if you will, hardware, the conic hardware, the pressure vessels on the bottom, you see that. We've actually got the liquid oxygen tank and hydrogen tank built for Artemis 3 already. So that's pretty exciting. I will say that every rocket gets a little bit delayed when it gets started, and And the big part, those tanks that you see down there are the largest hydrogen tanks ever built. It's complicated logistics when you get there, but we built the process really to build the tanks. And that's what took so long. It's not building the tanks that takes so long, it's setting up the factory and building the process to build those tanks. And I'm pleased to report that after we did the first one, which took quite a few years to build the new welding equipment and all that, the second ARTEMIS popped out of the factory, if you will, very quickly. Let's go to the next slide. I think we're about to transition. And oh, I've got more. If you keep going, one of the focuses is on engines, for instance. Really, it might not be understood, but the engines are the things that we didn't produce a lot of during shuttle. During shuttle, we reused those engines on every flight. And so because of that, we made them a Cadillac, if you will, and made them kind of expensive. And we would just take that engine off and reuse it. Now we want more performance out of that engine because we're going to throw it away. And we want it to be cheaper. And we've achieved those goals. We won't be using those achieved goals until mission 4 and beyond. But in 2 different contracts, we've set up cheaper engines and cheaper flights with some target prices that we're trying to hit for the vehicle as we go forward. And quite frankly, we're on schedule for all that. And so you can see stuff here that just shows you how real, as that question said, this program and this hardware is. We've got mission hardware well into ARTEMIS 2, 3, 4, and beyond. So let's go to the next one. All right, hey, this is a great test. We don't have to play the video. This test occurred during this COVID pandemic, and I was able to be out there in Utah and be at this test. This is our final full stage test. With liquid engines, you kind of pull them up and you start them up and you shut them back down and verify their operations. With solids, once you fire it, you're done. And so we count on production controls largely to make sure that we know what we're doing in our solid motors. And in this solid motor, we actually qualified some parts that are going to be used much later on, like an ARTEMIS 8. But this was the solid test to verify production of the current sets, the 1, 2, and 3 that are already built, and qualify parts to move beyond that. And so great test out in Promontory, Utah, that occurred in the first week of September. Let's go to, and we can stop the video. It's a good long video. We had a lot of good participation. We were social distance, but we did have a few folks out there, and I was able to be there. So, hey, so I'm going to turn it over to Rob. Rob has been working with you guys in this community. I'm privileged to be the chief engineer, and of course, my focus is getting that first step in that sustainable platform of rockets, and that is what I spend my day doing. But I am privileged to come and thank you for what you guys do for NASA and what you do for this agency. And thank you for listening to a rocket engineer talk about what he's doing. And I want Rob to pick it up. He's got a couple more charts to talk more specifically about how your missions map into what we do.
Okay, thank you, John.
John, thank you very much for being here. I really appreciate you making time. And good luck with the rest of the green test and the rest of the development for SLS.
Hey, thank you, Michael. I'm going to hang around. I know that there's some hard cutoffs, but I'm going to hang around for questions. And I'm going to let Rob carry the ball for a minute, if that's okay.
All righty. Go ahead, Rob.
All right. Well, as you know from the previous charts from Jim Kinnison and Wayne Schley, the vehicle that we're looking at for the Interstellar probe is the Block 2 vehicle. Right now, as you saw from previous slides, there is development work being done on the Bull boosters right now. That's actually on contract. The core stage is already built. And right now we're going through CDR for the exploration upper stage, and it also includes this interstage element right in the middle. We also have a contract in place to build the fairing, and that's a new development. And we're also developing the payload adapter. The big bottom line is that we're developing everything you see on this chart today. And so this is a vehicle that you can count on being available in the 2030s. And if you could go to the next slide, Michael, please. At the last workshop, I was approached by Ralph about what C3 curves he would like to see. At the time, I think I had 7 curves that he liked to see, that he wanted, and he needed an additional 17 run. And so I immediately ran to John Blevins to ask for for some engineering work to be done to have these generated, and he was gracious enough to allow us to do that. And we turned this around fairly quickly, I think within a month or so. As you can see, here's all the curves in front of you today, and it's the same data that Wayne presented in his presentation, I believe. I'd like to point out that when we build SLS, we're building it for a capability, a platform like John mentioned. We are optimizing the system to TLI, translunar injection. And if you were to look at the C3 curve here, the black line on the bottom is the block 2 nominal performance for C3 is greater than 60 kilometers squared per second squared. In order to get higher performance, to get very high C3 performance, added performance to even to Jupiter, additional stages are needed. So as you can see here, we've added 3 and 4 stages. We have a set of solids, the Castor 30B, 30 XLs, Orion 50 XLs, and also we ran a couple LOX hydrogen stages, the Centaur and Centaur D variants with Star 48 VVs and GXVs. I would like to also mention that when we quote performance within the SLS program, it is generally conservative. We don't like to give a performance number that you can only fly one day out of the year. We want to be able to fly all months of the year with many opportunities per month. So when we show you this performance, this is performance you can bank on and actually plan around to build these, to fly these missions. And I also put in the highlights here, the highlighted boxes to show you what options that Wayne Schley and Ralph were talking about, and Jim Kinnison as well, to show you the passive flyby for box 1, powered flyby, C3 area for box 2, and the solar overth for box 3. Go to the next slide, please. Michael, can you please go to the next slide?
I did. Maybe it's taking a second to upload.
Okay, there it is. I see it.
Okay.
All right, thank you, Michael. So I put this chart together, I think it was for the science, or no, it was the STMD workshop last year that Michael had asked me to attend. And this is just to show you what our trajectories look like when you have the fourth and third and fourth stage. Right here, you're seeing the trajectory profile during the burns, and also our 1 orbit loiter in low Earth orbit at 100 nautical miles. And I also put on here an equation for specific energy for the orbit. And I just want to point out that when you have a delta V, your launch vehicle is providing you quite a bit of delta V, you generally want to have that deep within your gravity well. And when your burns get very, very long, oftentimes you develop gravity losses along the way. And in order to compensate for that, there's 2 ways of doing that. One is to add more thrust, like a dual engine Centaur would help shorten that burn, for instance. Or you could add another orbit in place, another parking orbit, if you will, staging orbit. That is exactly what we did with Europa Clipper. Europa Clipper had too many losses when we did a direct insertion from the ground where we burned everything all at once. We actually now insert the ICPS into a very high orbit, about 300 nautical miles by 12 nautical miles, I believe. And that ICPS, the derived delta cryogenic second stage, we insert that stage completely full of propellant into that orbit, and we allow for 1 rev, and then we do a burn to go to Jupiter, the transjovian injection. And let's go to the next slide. I think that's all I have. I guess we're gonna wait a little bit for the slides to pop up. I just threw this in here, the statement from Carl Sagan: somewhere something incredible is waiting to be known, and that is for you all to discover. We are happy to build these rockets, to send these probes into deep space to help unravel the secrets of the solar system, the galaxy, the universe. We're all eagerly anticipating to see those results. And the next slide is essentially how you can follow us on social media. There's a variety of links that you can subscribe to get updates on SLS, so you can stay apprised of all the great things that are happening. And so thank you for your time. I greatly appreciate the opportunity to come forward in this workshop to present this material, to show you where we are, giving you our latest and greatest information. So with that, Are there any questions?
Rob and John, this is Ralph. I just wanted to thank you both for coming, and again, thank you so much for all the help over the years. And we'll see what we can do with this. Wouldn't be possible without you guys.
All right, thank you.
All righty. Do we have any questions for Rob, for John? I guess I love the videos that y'all been putting out, both the construction side and also the tests. Will there be some video, including the destructive test that you ran, which was fantastic to watch? I guess I expect you'll be putting up a video of the green test as well once that gets underway. And I'm curious, is that something people can watch in real time, or do you think it'll be an after the test sort of broadcast?
There, I'm unmuted. Yeah, John just had to drop off. He was just letting me know. I apologize. We are going to post all the material for the tests as they occur. So we're hoping as soon as we do the full duration burn test and maybe even the cryogenic loading test that's going to happen early December, we hope to get that material to you as soon as possible. And if you want, maybe we can have another webinar to show you what happens.
That'd be fantastic. We'd be happy to host that. and I'll do my part to stay as far away from any news articles about it, so I can be surprised by what happens during the test. So
very good. And the person that supports me within Stratcom, Bev Perry, she just left a message on chat saying that the whole green run test will be available, shown live on NASA TV, so everyone can sign in for that.
Fantastic. Fantastic.
I have a quick high-level question, Michael, if I may.
Sure.
I think this is important for everybody to hear, but we get a lot of people coming up to us and saying, hey, but you know, we know that the Starship is going to launch soon, so why don't you go with Starship instead? Or other big rockets out there? I know the answer to this question, but I think it's important that everybody hears. Ralph, Rob?
Well, so that Rob does not compromise himself, I'll just say, as you saw from the presentation, this is real. This exists. I mean, there have been some tests with Starship, but they're not to this level yet, not by a long shot. And we have been, certainly one of the things that we've been doing as we've been going along is we have been talking with Blue. We've been talking with SpaceX. The issue has been that they've got a lot of things that they're not really able or ready to kind of share publicly yet. And one of the key pieces of this has been Rob putting up with me and actually getting the crew down at Marshall to do all of these runs. And you saw the variety of curves that he had run, because I've been concerned all along that we really did, have a good idea of what the sides of this box looked like that we were trying to put this thing into. And it's been because of the support from Marshall, and this has been going on. I was looking back, Rob and the crew at Marshall have been actually supporting this project at no charge to us for 3 years now. And if it hadn't been for that, this study would really not have been possible to be at the level of potential realism for actually coming up with a mission that it currently is. Rob, if you would like to say anything else, we'll go ahead.
No, that's great. And thank you for fielding the question on Starship. I can't speak to anything about it other than that, yeah, it looks great. This thing that's out there in the desert that seems to make smoke and fire. I know we have a rigorous process behind SLS, and that's what we are showing you and demonstrating to you today. It's a flight proven approach to this hardware development, and I hope everyone takes that away from this presentation. Another thing to keep in mind about SLS, there's arguments that, well, why do you need SLS? Why do you need this 40-ton, 50-ton launch vehicle to the moon? And the reason for that is over the last 30 years, there have been numerous studies showing that if you want to go execute these lunar architecture missions, Mars missions, you need the very big launch vehicle. And fundamentally, the reason for that is you don't want to launch a whole lot. You don't want to have many launches to support one mission because your overall probability of mission success goes very far down, is greatly diminished by it. And that's why you want to be able to shoot 1 or 2 rockets to the moon, execute your mission, come back. Yes, if you look at a lot of the Mars architectures, there's 5 or 6 launches for SLS, but now you're talking about Starship, which is 13 launches for 1 SLS launch. So that becomes a problem. And I don't think that problem has fully come to fruition yet.
For my part, I believe that we as a community need to get behind not just one or the other. And by one, I mean a government rocket, and the other meaning the commercial rockets that are coming to, be very real. Falcon 9, Falcon Heavy, the work that Blue is doing, Starship eventually, and SLS all have a place. And I think we get too stuck in a either or debate driven by the media, who likes to create such discussions, and perhaps a handful of advocates who are trying to shut one or the other down in a way that's not very helpful. I mean, the reality is that the Falcon 9 and the rest of the products on the commercial side, they've got a market, and they're creating a market, and they're filling that market with a service. And I believe that as a community, we need to make sure that we don't disparage the good work that's been going on down at Marshall, to make sure that for the large exploration things that SLS can enable at the moon, and for big science missions that go to the outer solar system, we need this other capability. It's not either or, it's both and. And I think that we need to make sure that we're paying attention to the facts about what's going on at SLS, and not just some of the nasty stuff you see in the news from time to time. So,
well, let me just add that with respect to capability, I mean, there's some confusion out there, but I mean, if you're trying to get people to the moon, you need a lot of lift capability on a rocket, and right now there have been 2 things that have been built in the past that have that capability. One was the Saturn V. The other was the Soviet N-1. There were, the N-1 was from the Soviet part of the race to the moon. There were 4 launches. All 4 failed, which is why that the Soviets got out of the moon race. And now the only thing that's out there right now that's going to be ready to fly soon is the SLS. And this is, I mean, all 3 of these vehicles are really a very, very different class of vehicle from things like the Falcon Heavy. It's really it's a quantum jump up to getting to the moon. So, and it's hard. That's why it's called rocket science.
So, do we have any other questions from so many of our guests today? For Rob?
I have a question.
Yes, Glenn.
So, do you have a sense of the number of vehicles that are going to be available over the, what the manifest looks like, so that for I know that there's not just this community, but there's other communities that would like to use the SLS. We also hear about how much of this is going to be taken up by the manned program. So what's the possibilities? What are the probabilities of getting 1 or more of these vehicles over the next 5 or 10 years for missions like Interstellar Probe?
Thank you, Glenn. That's a very good question. So in terms of hardware availability, you can see we're already building plenty of hardware today. There are a number of limitations to building many SLSs in a given year. But right now, I believe we are focused on providing 2 SLSs per year. We're going to eventually work to getting up to that production rate. The limitation right now is not necessarily a core stage. I think we can do more than 2 a year for core stage. The limitation is going to be those RS-25 engines that we are restarting production right now. we never had to build so many so quickly for shuttle, and so it's a challenge for us to overcome. And we're hoping to implement some new technology with additive manufacturing and other things to help improve the production rate of those engines. And so that's going to be something that we strive for moving out. In terms of the near term, if you're referring indirectly to Europa Clipper, we do have hardware available. In fact, there's a LH2 tank down at NAF that we can't use for the manned spaceflight or human spaceflight. We're going to put women on the moon, so that'll be a great development. So the LH2 tank that we were building in early production, we found some weld issues where the factors of safety are not high enough for human spaceflight, but they are for robotic missions. So we can reuse some of that hardware and actually get another core stage out of it, which is a good development. We can use it for Europa Clipper, lander, whatever else is available. Right now, Clipper is it, from what I understand and what I'm told. Does that answer your question, Glenn?
It partially does, and I'm looking forward because Clipper obviously is the one that's becoming real. But you know, Interstellar Probe, we're thinking about when we have a need for that, and I'm aware of other missions that kind of have their eye on it. So I'm just trying to get an understand. So if you take away the number that are going to be for the human space flight, what's the probability of pulling these systems off? It looks like there's capability there, obviously for Clipper, but for Interstellar Probe, for something else. How might they fit into a schedule of vehicles availability to be used for these other missions?
From my perspective, I do what I'm told in terms of what Congress wants us to do. So I think we require political backing for each of these missions. Europa Clipper has substantial political backing, and that's why it's on our manifest, or I'm told it's on the manifest. There's another aspect, and that is the cooperation that happens between HEO and SMD. You know, Dr. Zhubukin has been very proactive in talking with Gerson Meyer in the past, and Lovero, and I think now Kathy Leaders. So I think with a healthy cooperation between the two organizations, I believe there is room for missions like Interstellar Probe and others.
Okay. Thank you. That's good to hear.
Right. And with that, Rob, thank you very much. And please do tell John again, we're very grateful he was able to join us. Great presentation.
Okay.
Good to see all the progress that's going on there. Okay, everybody. So we are a little bit over here. I suggest that we take a 10-minute break. Pontus, do you think that's sufficient? Okay, then it's 12:48. Let's get back here at 1 o'clock to let Pontus dive into the science traceability matrix and what all of your input this week has done to adjust, shift, and inform that. When he's done with that, we'll just do a quick kind of wrap up for the week. And one deep breath here, everybody. 10 more minutes, and I'll see you back here at 1 o'clock, and we'll close out this week. Thanks. Hi, everybody. We're going to get started again. Before we do, I'm going to ask you all to do a favor for me. So our sponsor office is the NASA Heliophysics Division, and Eric Posner is here with us today. Joe Smith, another member of the that office, has been on and off over the course of the week. Although I think Eric, has been here almost every day, and for almost every session that I've seen. They have a monthly report that goes into the Science Mission Directorate, and they've asked if we could take a picture of all of your shining faces, sort of a group photo, if you will, from the workshop. And at the beginning of this session here, could I ask you all to just turn on your cameras for a moment? And I'm going to just give me your best I love space smile. I'll take a couple of screenshots to collect all of this, and if it's all right with you, send it along to NASA headquarters. All righty, I see lots of people opening up here. Fantastic, and I think our peak day for this was Monday. We had 110 people on. We've got 48 on right now, but it'll still make a great set of photographs to send in. All righty. So just go ahead and give me your best I love space smile. And hold it, just keep holding it, because there's a lot going on here. We still got about 20 people who want to turn their cameras on. Maybe they're not back yet. Oh, they may not be back yet. Oh, let me think. Maybe give them another minute. 2, 3, 4, 5. Big group here. All righty. And all right, there we go. Very good. Thank you all. With that, I'm gonna pass the ball off to Pontus and let him take us into the home stretch here, talking about the science traceability matrix and sort of what we've all kind of collected and discovered and added into the discussion this week.
Thank you. Andrea, can you make me co-host? For some reason, it's disabled.
I'm afraid Michael will need to do that.
Michael, what do I owe you for making me co-host?
Good food in New York City next year when we hold the workshop again.
The Halal Brothers.
That's
remember?
right. Halal guys. Co-host. There you go.
Okay. Let me try this again. Here we go. Yeah, this works. Okay. Let's see if we can wrap this up. So as Michael said, this is going to be more of a science wrap up. There's been tremendous amount of discussion, tremendous amount of comments. I'm not going to make it too lengthy, I think, because I know everybody's tired. Here we go. All right. So
wait. Everybody's tired, but they're going to get mad at me. I only got the second of those 2 screenshots. Can we do this again? I'm sorry. It'll only take a second. Pontus, you have to stop sharing. Okay.
Yes, I know.
Forgive me. I thought I had it and I saw it, but then it did not stick. All right.
All right. Press harder this time.
All righty. Ready? 3, 2, 1. All righty. And one more time. 3, 2, 1. There we go. Okay. My apologies, everybody. I should never be the cameraman. We already know this.
Yes,
please proceed.
Okay. All right. Let me reshare. All right. So let's get this show on the road here. Let me see how I move this out of my way. There we go. Okay. So a lot of comments. I think we have already over 100 comments. I'm not going to talk about those here really, just some highlights. But let's talk about the science traceability really quickly here. My first lessons learned here is, yes, we did indeed get about, I think, 50 comments on the science traceability matrix overall. But I think it's true to say that once you put a monster spreadsheet like this online, nobody really looks at it because it's too big. So one of our actions on our side is to make this more compressed and more viewable, but the structure I think will remain the same. So depending on who's on here, you may want to chime up. I have just grabbed a few highlighted related science discussions here. Let's start with the fields group. There was a lot of talk, of course, about the need for low field magnetometer measurements. The flux gates that were flown on Voyager was sort of barely enough there. So there might be an option for technology development and improvements in that area to optimize that science. Obviously, for that group, it's the 50-meter wire antennas that are driving everything. They are required for getting the quasi-thermal noise to get the plasma densities. There was also talk about optional sounders. A lot of good discussion in that. And also in that, if Stuart or Bill is online, you also discussed the capabilities with shorter rigid antennas, but that's something also that we need to really put down on paper as well. For the particle group, the particle group ran over by, I can't remember, 1.5 hours maybe. Some of the takeaways there, one thing we need to discuss more is plasma charge states and how that also affects the allocations and the instruments that we have in mind. Another big one here that I think Casey brought up, if you look at the SDM, we have basically helio, planetary, astro. Are we stovepiping that traceability matrix too much? In my first gut reaction was, no, we don't. And a great example of that is, of course, Casey, is the dust, because we show the three facets or three sides of the dust question in the helio portion. That's the interaction with the heliosphere. It's the dust disk, and then in the astrophysics portion, it's the composition of dust that lends us information about the galaxy as a whole and their formation. So I think that works. And I'm going to sort of leave the floor open for comments from Casey and maybe some others on this stovepiping. Feel free to speak.
Well, if you'd like a comment from me, the stovepipe, this current stovepiping, I understand, because that's, if you will, that's a bit of how our sausage is made and how we're going to relate our science plans, our engineering plans to headquarters, 3 different divisions. If you attended either of my talks, you'll see that it actually made things very difficult because the science is so spread out across the STM and all these different colors and different divisions you have put in. As you just pointed out, we had to talk about extragalactic and galactic dust at one point, and then talk about solar system dust, and then talk about dust in the heliosheath and the heliopause. These were all different topics I brought together, so it was a very polyglot group that I had to address. And it does make the STM challenging, but I actually like the way that you responded. It was Michael Zemkov who brought up the question of whether it was too stovepiped in the dust science section. And your response was actually, I think, relatively telling. Not only did we, yes, maybe these are somewhat artificial boundaries because we're talking to headquarters and dust science covers all these different disciplines, but you basically said it showed how rich the dust science was and how important it is to this mission. And the fact that it isn't just in one science discipline, all the science disciplines are interested in it. And I think that's a fair response.
Yep. So basically my takeaway is that once we show those sort of 3 goals that are according to the divisions almost, we actually emphasize the cross-divisionality. So if there are no major objections, I would like to keep that structure.
No, they're not. In fact, I've gone so far as to adopt it. And you've heard us, for example, talk about this infrared spectral mapper. It's made me realize that maybe you've been talking about it mainly in the context of doing the solar system's debris disk. Well, it also is very important to actually seeing the role of dust in the heliosheath and the heliopause, as well as looking out in the galaxy and getting the extra galactic background light. It's going to cover all those different divisions we just talked about and different time portions of our mission. So I think it's actually a good way to go.
Yep.
And I'd like to double down on that a little bit. The composition of dust near dwarf planets and other trans-Neptunian objects is a huge boon to spectroscopy, so that you can literally ground truth by tasting the composition of the dust, what your infrared spectrometers are measuring on the surfaces of trans-Neptunian objects and dwarf planets.
Yeah, and that just came up in this mission, this workshop, that we need to add that to the STM.
Okay, very good. I need to go on here because I have a few slides now I want to go through. There was a whole lot of talk about priorities and increased priorities, of course, on the plasma wave antennas that I think they're already working on, but also on ENA low, NMS, and the Lyman alpha. If you are online, if you want to say a few comments about that, you can or cannot. I know this is being worked on. Is Andre online, perhaps?
Yes, I'm here.
Good.
Yeah, of course, our topical group on neutrals felt that, how to say, the prospects of the interstellar probe for in situ measuring the interstellar neutral material as we go out, and then in particular when we're outside the heliosphere, that this is really one of the main selling points of the whole mission, and that this should be stressed a bit more than it was in the previous version of the science traceability matrix. And of course, measuring neutrals can be done and probably must be done with different instruments. Actually, we have here listed several. So we have the ENA low imager, which is also very useful to measure the spatial distributions of the primary and secondaries of the interstellar neutrals. And of course, sort of what most people first have in their mind when they hear about neutrals, a neutral mass spectrometer, which is vital to actually get the chemical and isotopical composition of the whole stuff. And of course, also related to that is the Lyman alpha spectrograph, which is a different way of measuring neutrals, but it's also measuring neutrals. You get a line of sight of neutral hydrogen. So yeah.
Anything to add, Elena?
In addition to that, Lyman alpha gives you the global picture instead of just in situ.
Yeah, that they complement each other. So you have again this in situ and remote sensing.
Mm-hmm.
Yeah, we identified a number of questions that we think important questions that we think are missing in the STM. So it was very productive.
Okay, very good. Actually, one concrete outcome I think that would be very helpful is that if we can then formulate on a piece of paper that elaborated trade or science case, if you will, between, well, targeted to neutrals, and then we can use that trade, and we want to stick that in the next report.
Yeah, I will discuss with Andre to get together for 2 topical groups and discuss this important trade between ENA low, neutral mass, and Lyman alpha. We haven't done it yet.
So yeah, maybe it's at least our 2 groups, but since we're talking about ENA low, maybe also the ENA group by Bob should be involved.
Yes,
so.
Absolutely. Okay. Let me just go on. So,
but may I say something?
Yes, please.
Concerns phases. Seems to me that quite natural is that we have in fact inner heliosheaths and outer heliosheaths. I understand that everybody agrees as concerns the inner heliosheaths, but some discussion was about the outer heliosheaths. If we have bow shock, then definitely this bow shock is because the interstellar medium is supersonic and have this heliopause or the whole heliosphere, which is kind of obstacle. So outer heliosheath also is connected with the heliosphere. If even we don't have bow shock, still we have perturbed interstellar medium because of this fact that this obstacle, the interstellar flow must, how to say, obey, right? So seems to me that we still should keep these 2 regions, inner heliosheath and outer heliosheath, which means that between the heliopause and up to the whole perturbed interstellar meter, this is the interstellar medium. It is the outer heliosheaths.
Yes, I understand these comments, and we've gone back and forth with them. Okay, so let's discuss phases now for a little bit. So I think the whole problem is we don't know, right? We only know what is up through the heliopause and where the Voyagers are today, right? And I also think once this mission gets refined, of course, the phases may get refined, but I do think that for the study going forward, these three phases that I have on the screen, they make sense in the traceability matrix because they match up better with the science measurement requirements, and that's my target here. And so if you put the third phase beginning at the heliopause or so, that really takes you up to the unknown, so to speak. So also, if you look at the science traceability matrix for that third objective that we have, which is in the interstellar medium, that's actually where we put the questions about the nature of the bow shock, the hydrogen wall, and the rest out there. So it's more of lumping it logistically in the STM. Do we have any other major comments about these phases?
Yeah, this is John. Can you hear me?
Yes.
What about, since we are using SLS here, what about, sort of cross-cutting to human exploration, specifically the GCR measurements beyond the heliopause, as a benchmark, for models for a very long time, the lifetime of interstellar probe.
GCR measure, are you talking about the phase definitions here, or are you talking about just in general?
I guess I'm talking about adding, making sure that the connection to manned space is made at least through the GCR part of the measurements.
Yep, that's a connection that we could make in the traceability matrix and in other documents, of course.
Yes.
But,
particularly interstellar as being, the best upstream measurement of the
right.
cosmic rays.
Yep. Yeah. But if no other major objectives, I think we should just move on with these three definitions in distances, because it's about organizing not only the mission architecture study, but also the STM.
And
yeah, I think
Pontus,
that looks good, Pontus.
Yeah, and just this aligns with the definitions that Tom had recommended we follow earlier in the week. Yes.
Yes, it also follows what Bill Kurth and I think also Jonathan Slayman have said as well.
Not just Tom. Yes, so some of that's great. Thank you.
And I like.
Looks great.
Okay.
And before you move on, real quick,
Okay.
John Cooper, thank you very
One
much
quick
for
thing,
your...
this does kind of imply a noseward trajectory.
Can I add just a brief comment here, just to about these phases? The problem, I think, is that Interstellar, I think, is very good because, first of all, it's very unlikely that the spacecraft will actually enter into the pristine interstellar medium. This is too far away. And from this perspective, we'll be analyzing interstellar medium, perturbed, of course, somehow by the presence of the heliopause, but in different way for different energies, different particles, for neutrals and so on, pickup ions. So I think it just makes sense to have separately heliosphere and the heliosheath, but interstellar, we don't need to add outer heliosheath because probably this is all we have.
Yeah. It is what we know today. So
yeah,
I completely agree with that.
I agree completely. Yeah.
Bob, you had something. I'm sorry we cut you off.
Yeah, just that the 120 AU is going to assume a Voyager-like noseward trajectory, and I just don't want to be complicated if we go farther off into the flanks and have to change to
Yeah,
some estimate.
Yep, you're absolutely right. So baked into all of this, and also baked into to the SDM, is that example baseline direction. Of course, it's not exactly 90, it's not exactly 120, but the termination shock and the heliopause as we know it today, those are the boundaries. Okay, let me go on.
Okay.
Let's touch on mission success criteria. So as we talked about from the beginning, for now we set the mission success criteria as the threshold mission success criteria for simplicity, and to answer 2 questions under each objective. And then under each question, we must meet at least 1 priority 1 measurement. And so I've taken a quick look at the different combinations here. There are several different combinations, but there are just a few down here on the screen. And if you take a look at those combinations of measurements that could achieve mission success, they make sense. And also the strength here is that you have flexibility to combine different measurement types, of course. There was some concern that we set the floor of threshold mission too low. There's always this balance of if you set it too low, then you signal, of course, that, well, then you don't need much instruments to achieve the mission, which is not really true. And if you set it too high, on the other hand, you run into the problem of the all or nothing approach, where you don't allow for any flexibility in there. Have people had a chance to think about this more? To me, this sort of strikes the balance. We can sure refine it, but you look in the boxes here, you have a handful of instruments in each box. And they're sort of the usual suspects, if you will. And if you also look closely, they actually go through all of the instruments in the example model payload, if I'm not mistaken. Okay. All right. So let me repeat to everyone here, and I hope also Jim is online as well, and Gabe. So there's been a lot of sort of misconceptions here that that we're only doing a spinning or only doing a 3-axis. But let me repeat again, we're running 2 scenarios here. There's no scenario that is going to sort of win over the other. This is a trade study again. So let me repeat, the baseline study scenario that's under study now is spin stabilized. The normal spin rate is about 1 RPM, which seems to satisfy most of us. And it has the 50-meter plasma wave wire antennas, 4 of them. Oops, hang on, let me go back. After this workshop, we are going to study then the augmentation, which has the rigid 10-meter wire antennas. And again, let me repeat, this is a 3-axis dual mode spacecraft. And what do I mean by that? Well, it means that it will be spinning most of the time. And it will go into 3-axis steering or tracking mode once you do the flyby of the KBO. Once you're done with the flyby, you spin up again. And if you don't have any further flybys, you'll stay spinning. And that sort of requirement comes, of course, from a lot from the heliophysics, but it's also for stabilization purposes of the spacecraft.
We have a quick question from Gabe. Does 1 RPM, is that fast enough for the wire antennas?
Yes, yes. Let me loop back on that. As I understood it from Stuart and his group, you require about 5 RPM, at least when you deploy this. But then after you've deployed it, you then slow down gradually to 1 RPM. Is Stuart online? I don't think he is. I didn't see him.
He had to leave, Pontus.
Okay. Okay, so I just want to sort of reset that thinking again, that these are the 2 scenarios that we're studying.
Yeah, so Pontus, this is Jim. If I could just jump in for a second. I think what we'll find for the second case that we're working, that's the hybrid mode or dual mode. It's not just going to be during the planetary flybys when we do 3-axis, but there may be short periods of time when we want to do that for other reasons as well. There's a comment in the chat from Kirby about Astro.
Yes.
That's one possibility. The other possibility is there may be times for communication purposes, for instance, that it would be useful to spin down and use free access control to get higher data rates. I'd have to look at it. But point being, it's not that we would never spin down again, but there would be very limited times when we would. In between those limited times, would be long periods of times when we would be in spin mode. That makes sense?
Yep, absolutely.
Jim, this is Casey. I'm going to chime in for Astro. You're exactly right. If we want to, for example, make the look back image of the Zodi cloud around the sun with the planets in it that Contis and Ralph have been asking for, we need to have that be in 3-axis for that.
So the one that we will need to understand that comes out of this is what ConOps for that would look like. How often would you want to do that, and so forth? Because of course you're spinning propellant every time you spin up and spin down, right?
Astro has one other. Okay, sorry. Go ahead.
Now, I was just going to say, so we'll need to understand that as we're going into the engineering concept.
And Astro has one other question. 1 RPM may be a bit fast for for our applications in cruise. Is there a way to get to 0.1 RPM, or to slow down sometimes to that, but not stop?
Or the augmented scenario.
Even
for the augmented scenario.
Yes.
Yeah, for the augmented scenario, it's there would be no sort of hard and fast requirement on what the spin rate would have to be, other than just sort of what's the capability of the spacecraft on the upper end. The problem with the Helio case with the wires is we have to maintain a minimum spin rate to make sure we've got proper tension to keep them from going wacko on us.
I understand. So can you give us a better feeling for what that lower limit has to be?
Not right now. I can't. That's something we got to work, I think, with the folks who know about the wires.
Okay, so I'm just doing the best job of representing my constituency. I just want to point out is lower is better. Lower, much lower, factor 10 lower than 1 would be good if possible.
Yeah, I agree with that. My only concern is that I don't think that's going to be sufficient for keeping the antennas deployed.
Understood.
So Jim, this is Mike Zemkoff. I asked Ralph yesterday, and I'll ask you directly. We should probably talk at some point if that's possible.
Sure, happy to do it.
Yeah, so I have the information from Stuart about the minimum spin rate.
Thank you.
My memory says it was at 1 RPM, but I'm sure as we can dig that up again. And also just to what Casey said here, that sort of look back image that we've talked about, not yet really explored. I talked to Gabe about it a little bit, and Jim, is to be beyond the dust cloud and look back and scan with a potential IR detector to get that first image of the dust disk. And if that's possible, I think that would be very, very valuable for just selling a mission like this.
Yeah. So as I said before, in the dual mode or hybrid mode, something like that is certainly doable. It's a cost to propellant, so we just need to understand how often you'd want to do it, and just make sure we factor that into the delta V in the propellant budget.
Great. I think that would satisfy a lot of our needs. If we can get the spin rate down during cruise, that's the rest of it. Or if there are times like maybe once a few weeks every year, if we can slow down the spin rate, you don't have to stop, but slow it down so that Astro can do its science and then just speed up again. That's a good compromise we can probably live with.
Yep, this is a great dedicated discussion to have offline. Okay, so let me remind you of other scenarios that have been discussed. The idea of deploying 50-meter wire antennas after the KBO flyby, it came up actually last year, and we already last year said this is too high of a risk for a mission. We will not study it, but it will be documented in the report. Anything you want to add to that, Jim?
No, I think that's fine. We, as part of the documentation, what we got to think about is not just sort of the aging effects and things like that, but also the fact that you are now much further away from the Earth when you're trying to deploy these things. And so there are comm issues associated with that. Sort of worrying about imbalances. We're much more sensitive to imbalances in the wires and things like that. So we'll have to work through all of that and make sure we get it well documented.
Yeah, and for those of you who do not know, risk consequence 5 in mission language it's a loss of mission. So we don't really want to entertain a risk consequence of 5, of course. Other things that were talked about was, of course, the nose camera. Kirby led a great session on that. So I expect them to look a little bit closer on that, and that will also go into the next report. Rear view camera was, of course, discussed by Abby. There are some ideas on accommodation. Basically, the basic idea is simple. This would be viewing our solar system as an exoplanetary analog. And then there was a couple of others that came up. A D-spun platform has been discussed. The daughter spacecraft was talked about a whole lot. I'm not going to touch on it here, but it's not something that we're going to have a dedicated study for. But all of those will also be documented in the report.
Pontus, can you give us 30 seconds on the D-spun platform? Is it a ridiculous or is it a very elegant and simple hardware solution?
It is somewhere in between. It is still a high risk for, and Jim can fill me in here. What I'm worried about, but I'm a scientist, I'm worried about all the slip rings. You know, it sounds like a really simple and great idea from the beginning. There are other missions that have tried this compromise. And then in the very end, they've abandoned this compromise because of the risk. I would like to see a mission like this going to this new place. We got to maintain the low risk from the beginning. Jim, you have anything else to add?
No, I think that's exactly it. It's a mechanism. And so, you know, if you're talking about having a mechanism operating for, you know, 10 years, 20 years, up to 50 years, there are worries, right? And especially if it's a linchpin in your science. So I'm not enthused. I'll put it that way.
A good systems engineer knows when to threaten the science.
Yes.
Well, I'm scientists not trying to push something that is artificial or wacky. Is the TR level has ever been flown?
So Casey, this is Ralph. So certainly slip rings have been flown. I mean, there was Galileo, of course, had a D-spun platform, and if memory serves correctly, by the time that they finally figured out all of the power transmission connections they needed and all the signal connections that were needed, there were about 110 slip rings, and there were problems with arcing. They were really worried about the aging, and it was one of these things that it was. They made the decision, and then when they got into the details, they decided maybe this wasn't such a good idea after all. But they were way too far into the development of the spacecraft to change.
Well, also, especially if you look at long exposures, Galileo was not exactly the most stable because of that platform.
Good point.
That's a good point as well.
Excellent point.
So why don't we let Pontus go ahead and move on? And for our core team, we've been doing a lot of talking this week. Why don't we just let Pontus keep pushing this forward and see if our guests have other inputs they want to add in, since we've got each other as time goes on, but are going to have less of them.
That is absolutely. Thanks for keeping us straight. Don't be shy to speak up here, guys. Okay, I'm sort of getting in close to the end here, but one thing that has come up that I want everybody to keep thinking about here, because this is not really the STM. This is higher level than the STM. It's the success milestones along the way. I think in particular, a mission like this is very, very well suited for demonstrating these success milestones along the way. I've just scattered everything I can think of on the screen here. Oh, sorry, I have some automated timing in here. Hold on, go back. To start out, as we talked about before, the formation of the heliosphere and the heliospheric boundary starts really in the inner heliosphere with the evolution of with the ionization of interstellar neutrals and the evolution of pickup ions going out. We talked about that, so we must not forget that this first milestone is achieved on this journey outward here, of course. Then images of the heliospheric boundary as we move out. Those will be groundbreaking. We've never been that far from the sun taking ENA images. And then, of course, all of the milestones as we cross the boundary. Don't really need to talk about the importance of that. That's very high. And then the very next big milestone here, at least for heliophysics and also for dust, is to take that first external image of our home. It's the ENA image of the global heliosphere, and potentially also these IR images of the dust disk. And of course, the look back as well. And then you commence with the interstellar phase. And this is really when you start dipping your toes into galactic space. And part of this is reaching and figuring out the nature of a bioshock. Is it even there? Can we detect it? The other one is reaching the hydrogen wall. Interstellar probe reaches the wall. And of course, then you get into the properties of the interstellar cloud as well, collected chemical evolution, and all the other serendipitous discoveries that are waiting out there. Also along the way, I posted here is when you already start uncovering that first spectrum of the EBL and the improved understanding of the dust disk, and of course, potential KBO flybys. So I've posted a link of the Google Doc that we have here. And if anyone has any comments on this right now, I don't want to spend too much time on this. I mean, feel free to chime in here. But I really want to encourage to think about this so we can evolve it more. Okay. And you already saw this, but once we put all of this together, I mean, this keeps coming back to us. That, you know, the science that we're doing today and during this week and over the years is really clear. The disciplines doesn't really matter. This is really where the disciplines inevitably blur together. And we've shown a version of this very simplified Venn diagram before, but now it's taking more shape, I think. Any high-level comments on this?
So Pontus, one of the things you might want to think about, and I know we've kind of struggled with this, but, you know, to the extent that we're talking about the emergence of our habitable solar system, you know, at some level, and I'm not sure how you incorporate this, well, then there is a flavor of Earth science that is at the core of this thing, right? Not in a direct way, but in an indirect way, perhaps.
Right.
And figuring out how to incorporate that might be worth some thought.
Yes. Absolutely right, Ralph. And I know we talked about that before. Any other comments from the audience on this? Otherwise, I'll go on. I take this silence as violent agreement.
No, give them another minute or so to just think,
digest it,
and wanna speak up and let them be. Yes.
This is John again. Somehow indicating importance of application to human exploration.
Thank you. I think that's a good idea.
Stars, you know, we're emerging into the habitable system, you know, literally as well as figuratively.
Mm-hmm. Yep. I know I have a note taker, right?
I'm taking notes, Pontus.
That's what I thought. Thank you very much. That's what we agreed to.
You can breathe again, Pontus.
Well, it is. I hope this is still.
We've had a few people unmute themselves. Did they want to add in?
I have one question. Are you going to relate this mission to already existing missions, or missions that would exist anyway when Interstellar Probe will start its activity? What I mean here is there's plenty of air shower observatories which measure high energy cosmic ray fluxes. And those cosmic ray fluxes show actually the boundaries between the interstellar medium and solar wind. For example, the orientation of magnetic field, velocity of the BB plane is very nicely seen in that. The plane perpendicular to the BB plane, well, the heliotail probably is not an issue here, but it's definitely air shower experiments can be useful at complementing the aims of Interstellar Probe.
Yes, that's absolutely right. And in fact, we have captured that at I know at least, well, only one place in the science traceability matrix, and it's exactly what you talk about, is the galactic cosmic rays. But also what has been discussed is, of course, having an imaging mission sitting inside the heliosphere. Of course, once we get out there, I don't think IMAP will have survived that long. But that is also something that needs to be emphasized. And as usual, one shouldn't sort of bake it into the requirements because we can't, but one should emphasize the need for it. Solar wind observations goes without saying. I'm expecting there will be plenty of solar wind monitors by the time we get out there.
And do remember that ACE has been running for, Ralph, how many years?
Since what, 97, I guess?
So it's not impossible that IMAP, built along a similar architecture, parked at the same place, could still be running when Interstellar Probe gets out to 100 AU. Who knows?
Yep. Do we have any comments or takeaways from the younger audience? Feel free to speak up because you are the leaders of all of this.
You could call on people, Pontus.
Hey, let's do this. Could we have all of our early career and student participants raise their hands? We've got Eric, Daniel,
Sonny,
Michal and Elena, Kirby, Vikas, I believe we may have lost some of them to classes as the day went along. Lissith, what do you all think? What have you seen? How do you feel about this image itself? I mean, as in terms of like appealing to a much wider audience, you are probably a bit more in tune with what people like to see today than this gray-bearded man.
I guess I'll say something. I mean, not really that insightful, but I mean, I really like the graphics. They're really cool, and they like invoke like deep space and just like wonder, I guess. But I like that the mission really encapsulates many fields that we're looking to study and are very prevalent in space studies, heliophysics, planetary, and astrophysics, and astronomy. So,
thank you.
It's very promising.
Thank you.
Yeah, I can say something. I think it's really exciting. I really am really excited about what the mission can bring between what we know about dust in the solar system and in the ISM and at the edge. I think that's really unexplored, and any in situ measurements or nearby measurements could bring a lot of really important information that the space telescopes have not brought yet, and that is really relevant for our own origins. So I think it's really cool, and it has like all the heritage from Voyager, and I just think it's super exciting.
Thank you. I like how that lines up with Nikolai's comment about coordinating this with observations that would go on from other platforms at the same time. Thank you, Lissith.
Anyone else?
I have a specific science question, actually. What are the chances of finding organic molecules at any point during this mission? I mean, I'm not expecting proteins or anything, but any like simpler organic molecules.
Ooh, very interesting. Andre, do you have any insight in this?
Not, I would say, not on the top of my head, but of course, I read again the requirements for the neutral mass spectrometer, which is to measure molecules at least to masses 300 or better 1,000, so m/z, which is of course enough to measure, I would say, simple organic stuff. We're not talking about the amino acids and that stuff, but let's say some rather simple organic molecules we definitely could measure if they are out there. Of course, it is well known if we ever get close to a comet or stuff like that, then you find a lot of organic molecules. In, let's say, in free space, I don't know, there will be some, but I would take some moment to actually study and, well, make any educated guess about the numbers and then say, how long we have to integrate to be sensitive to whatever comes along our way.
So Pontus, you actually bring up a very good question, and this was brought up initially by what was called the Interstellar Probe Science and Technology Definition Team out in 1999. And the question was raised then, and it was noted that the problem is that most of these complicated organics are not bound that tightly. And so with the speed of the spacecraft, the real challenge is how do you slow them down enough so that you don't tear them apart when you're getting them into the instrument.
I have a comment. Oh, sorry.
Yeah, go ahead. Go ahead.
Yeah, I just wanted to comment also on Vikas' question. It's not really a molecule anymore, but a dust detector can detect particles down to 10 nanometer. That's only 10 times as large as a C60 molecule. So we can really detect particles that are not able to penetrate the heliosphere and that are out there. So that is a huge thing, I think. But I don't know if you call it a molecule or dust, you know?
It will rip them apart in atoms, but that's a very good point. At the velocities we encounter them, we won't actually get the molecules anymore. I've actually pinged Jamie on this directly for the IDA design, for example, but it will be able to measure very small ones, yes.
I think this touches on a very, very extremely important point. And it's the fact that once we get out there, there are discoveries that we're going to make that we don't even have questions for.
Yeah, and maybe one last point about this. Dust detector will also be very helpful, of course. The problem of, fragmenting bigger molecules when you have a mass spectrometer, you have this problem everywhere anyway. So if you do any flyby at icy moons or a comet, you have this problem all the time that you need to study the whole fragmentation pattern that you get.
Right.
You cannot escape this problem anyway, but then we will do our best, of course, to glue together sort of the fragments and say what are the parent molecules.
Right. I mean, you'll be able to get carbon, hydrogen, oxygen ratios and say, oh, that was a carbohydrate, or if there's nitrogen there, it was probably a acid.
But I also want to make the point of infrared spectroscopy revealing organic molecules on the surfaces of trans-Neptunian objects and dwarf planets. Just like we see on Pluto behind me, the whole equatorial band around Pluto is it's organic gunk, tholin, on the surface from irradiated methane in the atmosphere.
Dude, you've got a really good Zoom link.
And Caitlin
Pluto's
Ahrens
right behind you.
And Caitlin Ahrens at the last workshop talked a bit about that. She's been leading the charge on that. So we should probably invite, and she's a young career scientist too. I'm not sure if she's on right now.
So Andre talked about the neutral mass spectrometer, but what about charged mass spectrometers? You would at least get an energy per charge measurement, even if it's a molecule from that. I guess you would need post-acceleration to measure it, but you would get a good idea of at least what the total content of that molecule is in AMU.
That's a good point. Very good point. So Ralph, I mean, the question about the impact speed and dissociating the molecules and the organics is an old one. I think, I'm not totally sure, but there have been studies that also tell us that breakup is not as violent as we think. And I'm also referring to some of the APL studies that we did for some of the proposals that Rob Gold was involved in, right?
Well, I think you're right. And I mean, I think it gets into exactly how complicated a structure you're looking at. I mean, for example, if you're trying to look at left versus right chirality, you got a problem if you break everything up. But there was, like I say, it was looked at. Part of the problem was there was no development money at the time for instrumentation to really dig into it any further. And so I don't know. I mean, there may be some other things out there, perhaps either in our field or in some other fields where there have been some advances made where there might be some applicability there. But most of what we looked at was, gee, you need to maybe have some sort of a trap, an electromagnetic trap where you can slow these things down and then take a look at them. But that's
they did get funding a few years ago for a conical collection device that would decrease the impact energy because of the slope of the collection zone. And Rob and some folks at NASA Ames they got funding to do that for an Enceladus mission concept.
Yeah, but
that's
they
something we can
probably
look
weren't
into.
going 35 kilometers a second.
No, it's 40.
No, like I think they were trying to collect samples at about 10 times less speed than that.
Can you briefly educate me? If we talk about 8 AU per year, how many kilometers per second is this?
About 36 kilometers per second.
36. All right, yeah, that's an order of magnitude larger of what you usually have if we do flybys. That, for instance, for Clipper and the Juice, we're talking about 2 or 4 or 6 kilometers per second.
Exactly. Yes.
Velocity.
But if you convert that kinetic energy into EV per molecule, you're going to find out it's going to be on the order of 10 to 100. It's a lot. That's the bonds. So may I suggest something we try and instead with do what Stardust did. Stardust learned that they had to actually do a lot of ground testing and actually simulate how particles would actually have impacted their aerogel in flight. So maybe one of the things we want to think about is actually having a ground setup that mimics our instruments in flight and be doing some of these shooting different molecules into it.
Yeah, calibrate the whole thing. Yeah.
Could this be made into a student experiment? Anyway, very lovely discussion. I have 2 more slides that are a bit drier, but I think we have to move on, right, Michael?
Can I have one question?
Correct.
Please.
Do we consider some squeeze to measure the magnetic field?
Say that again.
Do we consider some squids to measure magnetic fields? It's linked to magnetometry.
I don't know what those are.
Squids are superconducting quantum interference magnetometers.
Yes.
Right.
Squids.
Yes.
Okay. It currently not on the table. No. I have to admit I don't know much about them.
I think people have looked at them in the past about putting them on spacecraft, and there have been, I don't remember the thread exactly, but there have always been some issues about doing that. I'd have to go back and look at the literature, but people have talked about it. But it's been difficult because of some of the other things that you can't control on a spacecraft that you can in the laboratory environment.
Okay, let me go on. Thanks so much for all the input here. I know it's Friday and it's late for some people, so let's try to wrap this up here. I have 2 other slides and discussion points. So next steps in the meetings, right? So the next study steps on our side on a very high level is, of course, we're going to incorporate all the 100 comments that we got and the suggested changes into the SDM. Then on the architecture side, and Jim, you can fill me in here, we can conclude the Helio baseline mission architecture study and then begin the augmented mission architecture study. Is there anything else you want to add to that, Jim, quickly?
Nope, you got it.
Okay, great. Then we have the next kind of meetings here. So let's spend a minute on this. I would like to encourage all the topical group leads to continue the telecons. They've been really successful and productive. Elena has already talked about having monthly tag ups for the white paper coordination. And an idea that has recurred many times is to have an intermediate mini workshop in the late spring. Any opinions on that? Any thumbs up? Good. Because I think that's really needed for us, not only for coordinating the science, but also touching up where we're going with the architecture study. It could be 1 or 2 days. So I think we'll sit down and plan for something simple like that. And as you all know, next year we'll have the other exploration workshop, the full workshop, and the key word there is closure. Another thing that I think we want to have is regular tag ups with topical group leads. We've had them in preparation for this workshop. They worked really well. And I think what we want to do is to reach back to the topical group leads and see if we can have them maybe on a bi-monthly basis where we're just get together with the topical group leads and the key members of those groups to tag up on pretty much all the science aspect of this.
Are you talking about monthly or bi-monthly?
I think bi-monthly to start with, because there are a lot of other sort of small tag ups in between.
Yeah.
Something where we get everybody together, not just group leads, but also some key members of the group, and sort of open up a little bit more.
All right.
Mm-hmm. Okay. This is a list of very high level group actions. So the way I think we want to handle this is that the group leads, you have a great set of comments and actions, and I expect you to coordinate all of those further discussions among the topical groups, right? And in the STM, of course, we have to continue to develop that, especially measurement requirements. That fifth column or fourth column in there is currently blank in many places. I would like to have more details in there. Of course, we fill it in on our side as much as we can. The third bullet here is pretty important, I think. We heard a lot of discussions on further science here. I would like to loop back to people to ask them if the mass allocations are still sufficient on the individual instrument level. For example, we talked about plasma charge states, GCR capabilities, and geometrical factors. We have certain individual mass allocations on the instrument level for those, but we got to make sure that those are realistic. So please, in the topical group leads, please look back on that and look at it. Then two very important points. You've seen the two payloads. So number one, we sort of already discussed this, but number one, take a look at the Helio baseline payload. There are things missing in that Helio baseline payload. The ENA-LO is not there. Document the science trade-offs. And I heard now that getting together with ENA-LO, Lyman Alpha, and the neutrals group is a good discussion to be had. Then also discuss and also document the science trade-off between the Helio and the augmentation. That is also something that is needed. We've heard some of that, but we need that down on a piece of paper. And I think that's pretty much it. The rest we have discussed, but I want to take one last step back and ask everybody, given everything you've heard and discussed, do we have some level of consensus that we're heading in the right direction? Is there anything major that is missing? Do we need to nudge the direction? And remember, shortly after this workshop, we need to finalize at least the Helio portion of the STM. Okay, any comments, go backs?
Please speak up now, because if you don't, we're going to finalize them.
Yeah. How many do we have in line here? I have trouble counting.
It's 46 right now.
46. So if we're not heading in the right direction and you want to nudge it, please let us know.
How about we do this too? The question at the moment is, are we going in the right direction or not? If you feel positive, moderate, or negative on that, type it in the chat. Type it in the chat. I mean, it's okay to tell us that we're off base. It's okay to tell us that we're a bit askew. It's okay to tell us that we're fantastic.
This is John. You might add to GCR capabilities and radiation noise. It's really very important, when you get out in the interstellar medium for the superthermal measurements.
Yes, absolutely. I think that's already been noted. That's great, John. Tends to be forgotten.
I have a question. Are there any plans to use the spectrometer to check for any potential new elements or any heavy metals in our solar system?
in the current configuration, the short answer is no. These are requirements based on known elements.
Which spectrometer?
Just infrared light using spectroscopy.
I think the issue there is geometric factor, that as you go out to some of these other elements, which would likely be extremely rare, because otherwise we would pick them up anyway. You end up having to be able to integrate for very, very, very long times and actually have very, very large geometric factors, and those tend to drive your mass and your size of the instrument. I know that there's some, for example, after about 15 years of integration, there was some rare isotope. There was a rare isotope of iron that had actually been detected on the ACE spacecraft. But again, a very, very long time, and that was a very large geometric factor spectrometer. So there's some of these things that we're just simply not going to be able to do because of the overall mass and the power that are associated. But it's a good thing to note, because we need to be able to document both what we can't do and why we think we can't do them, as well as what we think that we can do.
I think the specific question was actually about IR spectrometry.
Sorry.
Yeah.
And I would just throw out the ideas that in general, we're going to design, just as we've already heard, for what we think is out there, but that's no fun. One of the things, we certainly want to be discovering new things, and we can point to Rosetta at Comet 67P. They discovered O2, a molecule that nobody expected to be there. And we will certainly keep our eyes open, make the best instruments we can. And I'm not trying to just say a motherhood statement. And I hope we've got some unexpected things that rock our socks and change our paradigms. So if there's a line of trans-uranium species and for some reason pops up in our infrared spectrum, I hope that you or somebody like you finds it. But we can only do so much, as you heard. We have some limitations to our spacecraft.
And if I might use that as a jumping off point to kind of wrap things up. Heading out to New York last year for the workshop, I had the pleasure to stop by in Princeton and sit down with Freeman Dyson and talk some more about this mission with him. And one of the things that the only thing that he told me, like we talked about a bunch of different things, but the only thing that he told me was, you all have to make sure that what you do is leave this mission in a position where you can be open to discovery. That if you just put down a bunch of measurements that you're going to make, and it's all things that we know we can do and want to do, that we've kind of closed ourselves off to discovery. But if we can craft this in a way where we're open to discovery, then we'll really have done something important. And that's a real challenge. It's a real challenge with how missions are crafted and formulated and then funded. But it's a good jumping off point. All right, Pontus, you didn't have any more slides, did you?
No, absolutely not.
Okay,
Everybody's
go ahead
tired, including myself.
Okay,
this
cool.
is a great job for everyone. Thank you.
All righty.
Thank you, Pontus. Can I say one thing really quick? It won't be long.
Really quick, go for it.
The Google Docs that we all opened up for each of the individual discussions are going to stay open for the next few weeks. If you have any more comments, we want them. Please, these are living documents, and please add to them.
Yes, and in fact, that was going to be my first point as we wrap up. We're gonna keep them open, as Casey said, for 2 weeks. And we need more of your input, more of your comments on them. As he said, thank you, Casey, for bringing that up. The white paper meetings, I think, are going to be essential to overall success. Elena, thank you for leading the charge today and helping to coordinate that in the future. We as a study team at APL, we're on the cusp of releasing not one but 2 large reports to the sponsor on the technical progress over the last year and a half. And once NASA has had a chance to review those, I believe large portions, if not their entirety, are going to be released. And all of this will definitely have links to on our website. Speaking of the website, all of the presentations, including the ones that were put together for today, are available on the website, will be available on the website. The one like Pontus's will be added to the website now. And all the video recordings that we took over the course of the week as we recorded the Zoom, those will also be trimmed down a little bit to get rid of the empty space at the beginning and the end, and then made available here. If you'd like to share them with people, if you'd like to look at them yourselves to remind yourself of the discussions, we really want to make the website a sort of a central place, a clearinghouse of information for all of these discussions. We as a team internally are going to release an after action report, basically a summary of what happened this week. And we'll be kind of going through our notes over the next week or so, and hope to get that out about 2 weeks from today. And we may reach out to some of you to clarify some points as we do that. So don't be surprised if you hear from us. And finally, if you liked participating in this, if you think that we're on the right track, moderately on the right track, positively going in the absolute best direction that anybody could think of, we really want you to share this with your friends, with your family, with your colleagues, and help us to grow this initiative, this effort, this community, especially with younger folks. We are so pleased that so many students registered for this conference, that so many participated in it. And at one point, I was a very young systems engineer on a planetary mission and thought that it was just fantastic. And when Ralph McNutt first asked me to start helping out with this project and said we need to recruit young people, after a few minutes of discussion, he said, no, we need to reach down into middle schools and start getting them excited about this. This is going to take multiple generations, and I can't think of a better thing for any of us to spend our time on than something that far outlives our own careers.
Thank you very much.
Thank you, Roma. It's very good that you're here.
Oh yes, it was. I am very happy to be here. So thanks a lot for the fantastic meeting.
And I hope our paths cross soon, both yours and all of yours and mine. It's great to see you. It's great to have this positive energy flowing in, and I hope all of you and yours do well over the coming months and weeks. And with that, I think we wrap. Thank you all so much for your participation. We're very grateful.
Yes, thank you all.
Thank you.
Have a great weekend. Thank you.
You too. Thank you all.
Thank you all.
Thank you, everyone.
Andrea, bye-bye.
Bye-bye.
Goodbye. Take care. Everybody stay safe and healthy.
Bye.
Bye.
Thank you.
Thanksgiving.
Bye.
Happy Thanksgiving indeed.
Ni hao, bye-bye.
Bye-bye.
Michael, Pontus, Ralph, Elena, we have a wrap up, just a small group wrap up meeting.
Yep. We can use the one that Alice set up. Yes.
I had a scheduled. You should all have an invitation to
Oh,
it.
a separate one.
Okay.
Very good.
Organized. Okay.
Very good.
See you on the other side.
You there,
Andrea? If you need me, you need to send me the invite to the wrap up.
Michael, I only invited the regular meeting planners to that meeting. Should I have Jim come as well?
Jim, if you want to join us, yes. Why don't you go ahead and shoot it, and then he can. If you want to join us for a couple minutes, it's just going to be a quick wrap up.
Honestly, I'm happy not to.
Then we'll see you later. You have a good you have a good weekend.
Go ahead and send it to me. I'll join you for a few minutes. I'm just.
Yeah, it's okay.
Oh. Andrea, I'm sorry. When did you send it? I think I can't find it.
All right, I'm gonna resend it to you.
Oh, please, yeah. I think I saw it, but I can't find it at this moment.
There we go. Voila.
Awesome, thank you.
Thank
See
you.
you there.
All right. I'm gonna hop off and go there. Is there anything that you need, Michael?
Nope. Oh, one thing. I'm gonna hit. When I hit end, it'll record this here. This is a longer one, so if my computer gets wonky, I might simply get on by my phone. So if it takes me a couple minutes to get there, you'll know why.
All righty. Thanks for the heads up.
You bet. Onward and upward.